In this video, we'll study Taylor polynomials, their applications, and approximations. As a quick overview, we will learn how to rewrite polynomials as Taylor polynomials, which will be significantly helpful when we want to center a function around a particular constant. We will learn how to use Taylor polynomials to approximate other functions. And finally, we'll write functions as a Maclaurin series. Let's start by trying to find the Taylor polynomial for a given polynomial with the function f of x. For f of x equaling 2x to the third minus 3x squared plus 4x minus 5, a third order Taylor polynomial is the identical function, just written in ascending order. So you can write standard polynomials exactly as Taylor polynomials. However, this is not very interesting. What we would like to show is that you can write a function centered around any point, and that is where Taylor polynomials comes into play. Now what we want to do is find a Taylor polynomial for f of x centered around x equals 1. That's going to help us take that approximation near 1 instead of near 0. To do this, we're going to set up the function at 1 and evaluate it. That gives us our a0 term. We then take the first derivative and evaluate at x equals 1. This gives us our a1 term. We continue this process until we can rewrite our original function as a Taylor polynomial centered about x equals 1. To verify our results of our Taylor polynomial, we have plotted our original function f of x as the red line. Now, we should be able to see our functions plotted out right on top of each other, even though we now have the function centered around x equals 1. The reason why we choose to recenter our function comes back to our earlier example of the sine function. We showed that as we got further away from 0 degrees with sine, going from 10 to 45, we required more terms to approximate sine to a higher degree of accuracy. If we were to approximate the function f of x, it would do well around the point 0. But in this case, what we are allowed to do is now approximate well around a different centered point. However, this illustrates the ability to change the area about which we are approximating. Now I want to talk about how Taylor series allows us to approximate functions that are non-polynomials. A good example is the sine function. We've seen that sine can be represented by an infinite sum of odd order polynomial terms. The first order is x to the first power, and the seventh order is x to the seventh. Okay? If we write p sub 1, we get just that the Taylor polynomial is equal to x. If I write p sub 2, that is x plus a 0 second order term. So the pertinent ones for sine are the odd Taylor polynomial sums. What we have here is we have an approximation of sine at the angle of 10 degrees. We can write that as pi over 18, and we are given this long decimal place number. Notice that if I evaluate the Taylor polynomial P1, I am just evaluating pi over 18. P3 instead replaces every x value for pi over 18. And lastly, the fifth Taylor polynomial is just given. I have highlighted in red the decimal places which differ from the exact answer. You can see that a linear approximation for a 10 degrees angle errors only in the 0.5%. And when we take the fifth term polynomial, we get 5 times 10 to the negative 7th percent. So it does not take a lot, only really 3 polynomial terms to approximate sine at an angle below 10 very well. So let's ask the question, what happens when you approximate away from where the Taylor polynomial series is centered? Sine of 45 degrees is the square root of 2 over 2, or written out in its decimal form, you can see this. I've evaluated the Taylor polynomial for the first, third, and fifth terms. And as we can see, the error goes from 11% for a linear approximation and improves down to 5 parts in 1,000% on the fifth Taylor series polynomial. The last topic that I want to cover today is how we can find a Maclaurin series for a general function. Now we have to look for functions that are similar to known Maclaurin series and see if we can rewrite them and then do a bit of u substitution. So let's start with the function f of x is equal to the exponential of 2x minus 1 divided by 3. Recall that we already know the Maclaurin series for the exponential of x is the infinite sum of x to the n divided by n factorial. What we want to do is rewrite the function of x. By multiplying by 3 and bringing the negative 1 over to the other side, I now have the exponential by itself. Now, we can replace that e to the 2x with a Maclaurin series with the argument being inside that series. So notice now x is 2x in our Maclaurin series for the exponential. This is equal to 3 times the function plus 1. These next few steps are going to help us simplify the function. So I'm going to evaluate our infinite sum at n equals 0, and then leave the rest of the sum starting at my index n equals 1. 2x raised to the 0th power divided by 0 factorial ends up being 1 over 1. Now I can notice that there is a 1 on both sides of the equation. Having those cancel out, I'm left with 3 f of x equaling my Maclaurin series. Dividing through by 3, and now I have the function written as a Maclaurin series. To end, I want to review 3 more practice problems where we take a function and rewrite it as a Maclaurin series. So the first one that I want to talk about is x squared times cosine of x. I can write that as x squared times the sum of n equaling 0 to infinity of negative 1 raised to the n power times x raised to the 2n divided by 2n factorial. I then can multiply the x squared through my Maclaurin series. 2n becomes 2n plus 2, and that is the Maclaurin series for x squared times cosine of x. We know the Maclaurin series for e to the x, we are going to multiply an x through, which is going to change the index of the exponential. Finally, we have 7 times the sum of x raised to the n plus 1 divided by n factorial. Finally, I want to write the function x divided by 1 minus x to the third in its Maclaurin series. We know the Maclaurin series for 1 divided by 1 minus x. So I'm obviously going to factor out an x value. But what do I do with the x to the third power in the denominator? Like some of our previous problems, I'm going to do a u substitution. I'm going to call x to the third power u and work from there. This allows us to set up the Maclaurin series as x times u raised to the n. This simplifies down to u to the n plus 1. What we need to do now is undo our u substitution. Now, when I have an exponential raised to an exponential, that is when they are multiplied together, and the result gives me x raised to the 3n plus 3. And that is the Maclaurin series for this function. Remember, polynomials can be exactly written as Taylor polynomials centered about any point. We can recenter a Taylor polynomials to improve our approximation near that point. This helps us to reduce the number of terms we need to approximate the original function. Many functions can be rewritten as some modified version of the Maclaurin series.